So here we discussed what is an expected value of a random variable, which is defined to be summation x into p of x when x is a discrete random variable, and if it is continuous it will be given by integral x into f of x dx. Similarly, we define expected value of a function of random variable. So that is what expected value of g of x. And you could see that this x is replaced with g of x simply, summation g of x into p of x when x is discrete, whereas integral g of x into f of x dx when x is continuous random variable. Okay, and next we saw the properties of expected value of x. So if you look at expected value of ax plus b, where x is a random variable, a and b are arbitrary constants. So where here a comma b, these are arbitrary constants. Let me say that they belongs to real numbers. So then expected value of ax plus b equal to a into expected value of x plus b. Okay, and similarly if x and y are any two random variables over the sample space, then we can say expected value of x plus y, which will be same as expected value of x plus expected value of y. And this result is true even if you take n random variables. So you have n random variables, and you'd like to know what is the mean of some of the random variables. So that will be same as sum of the means, that is expected value of x1 plus x2 plus and so on. This is equal to expected value of x1 plus expected value of x2 plus and so on, expected value of xn. So this is what for any random variables. And one more important property, expected value of x into y. So this is about expected value of x into y. Now the question is, can I say that this will be equal to expected value of x and expected value of y? Is it true always? The answer is no. It is not true always. It is true for a specific case only. When you know that x and y are independent, then only this result is true. But if x and y are dependent, they may not be equal. So let me write, let x and y be two independent random variables then expected value of x into y, this will be same as expected value of x into expected value of y. Be careful, here x and y are independent, then only I can write this result. Okay, to look at the proof of this result, we must understand what are bivariate random variables and joint probability density functions. So from that you can easily prove this result. Okay, so these are the properties of expected value of x. So the next we can define what is variance of a random variable. So the variance is actually, see, when you have a distribution, some probability distribution, so you'd like to see what is the mean of that distribution, the weighted average. Okay, so the expected value of the distribution, this is what you'd like to see. Now the question is, so how sure are you about this expected value? It means what is the deviation from the actual value to the expected value? That's what I'd like to know. It means here when you perform a random experiment, ideally we are saying that this is the expected value, or you can expect the value of the random variable to be in this range. So now what is the maximum deviation I can take? It means what is a variance or the standard deviation. That's what we call the standard deviation, sigma. So now what I'm looking is what is the error in the expected value. In other words, I'd like to see what is the distance between the actual value and the expected value. Okay, so let me define this to be a new random variable y. So now y is equal to x minus nu. See, where we define expected value of x to be nu. Nu is a constant. Okay. So now the question is, so what is this difference? And what is the expected value of this difference? So now I'm interested in knowing the expected value of y. Okay. So now here you want just an error kind of thing. So in that case, you can take the absolute value. So that is e of absolute value of x minus u. But you know, this absolute value is not always good when you want to extend the results for higher dimensions and when it involves derivatives, integration and all. So especially if you have derivatives there, we don't prefer this modulus function. Okay, so instead of taking modulus function, you try to choose some guy who is positive, and again you try to get back to the expected value of y. What I mean, instead of dealing with modulus of x minus nu, you better deal with x minus nu whole square, and you find what is its expected value, and then you take its square root. So this is how you can get the deviation, and that's what we call standard deviation. Okay, so now let me define my random variable, that is y, or you can take it as z, that's equal to y square, which is what, x minus nu whole square. So now you see what is the expected value of z. So that is what the expected value of x minus nu whole square. Okay, and this is what we call variance of x. Okay, so let me give the definition of variance now. Variance of a random variable x is defined as like this. So variance of x, which is equal to expected value of x minus nu. Instead of writing nu, let me write expected value of x whole square. Okay, and I hope you can simplify this guy, and you can, or let me write it like this: expected value of, this is nothing but x minus nu whole square, and if you expand it, this is expected value of x square plus nu square minus 2x nu. So now this is same as expected value of x square from the second property of this expected value of x plus y, which is same as expected value of x plus expected value of y. So using that, I am writing, so this is expected value of nu square. Nu square is a constant, so you can take it out, and expected value of 1, you can take it as 1, minus 2 nu into expected value of x, and you could see this is same as expected value of x square. This is plus nu square minus 2 nu square. So finally this is what we get: expected value of x square minus nu square. But we know what is nu. Nu is nothing but expected value of x. Therefore variance of x, this is defined to be expected value of x square minus expected value of x whole square. So this is the formula we are going to use it. So whenever if you want to find the variance of x, so you simply take expected value of x square, then you subtract it from then you subtract this expected value of x whole square. Okay, and we define standard deviation. Standard deviation of x, and we denote we denote that with sigma, where sigma is equal to square root of variance of x. Okay, so that's what no need to write this guy. Okay, let me write it. So that's what square root of expected value of x minus nu whole square. That's it. So this is what we call the standard deviation. So this standard deviation will tell you, like, so distribution about the mean, like how far it's going to be, minus delta, like expected value minus delta to expected value plus delta. Okay, so it means your expected value can so minimum it can go up to here and maximum it can go up to there. So that's what you can say. Okay, now let us see the properties of variance of x. So the first we'll look at the linear property. So what can we say about variance of ax plus b? Okay, so this is what we are interested in knowing. So for that, let me do one thing. Let me consider a new random variable y equal to ax plus b. Now first let's see this is what we'd like to know. What is the variance of y? Okay, but we know formula for variance of a random variable. So variance of y, this will be given by expected value of y minus expected value of y so this square, yeah, you know what is y, and let me write what is expected value of y. So that's what exactly expected value of ax plus b, and from the properties I know this can be written